Hello, my name is Tiffany, and today I'll be discussing semiconductor physics and its fabrication process. I was motivated to do this project because I've had some previous work experience in this industry, specifically in the Silicon Valley. And my work mainly supported the development and maintenance of externally manufactured components of high-performance analog semiconductors used in wireless networking. Specifically, I did post-reliability stressing of components like multi-module chips and did cross-section analyses for structure validation. Given my experience, you may wonder, oh, where does the term Silicon Valley originate from? This term was first adopted in the early 1970s in South San Francisco due to its association with the silicon transistor. This vital electronic component is an example of a semiconductor. Now you may wonder, what are semiconductors? Well, they are the brains to many modern electronics and are widely used in familiar appliances such as smartphones, personal computers, and digital cameras. They are the driving force in many industries such as healthcare, military systems, and aerospace, and are valued for their balance between conducting and insulating properties. In addition, semiconductors enable technologies critical to national security, economic growth, and global competitiveness. Unfortunately, this industry is facing disruptions in the supply chains due to the pandemic, natural disasters, and trade tensions, thus resulting in product shortages, reduced revenues, and higher prices. Despite these detrimental effects, the understanding of this industry's impact proliferates into every sector of electronics and everyday life. Thus, it is important to know how semiconductors operate and their fabrication process. Common semiconductor materials such as silicon and germanium have electrical properties between an insulator and a conductor, hence the name semiconductor. In order to understand them, we must first need to understand what determines some materials as conductors and other materials as insulators. Take this diagram on the left, for example. The height of this image represents electron energy. Inside this material, some energy levels are allowed, in this case, energy level 5, whereas other energy levels are forbidden. In this diagram, electrons are allowed in energy levels at the top and the bottom, but there's a large gap of forbidden energy levels in between. In this example, the top band of allowable energy levels is partially full, giving electrons to move around. As a result, this material is an example of an electrical conductor. On the right, the bottom energy band is completely filled and the top band is completely empty. Here, the electrons have no room to move around. As a result, this material is an example of an electrical insulator. Now suppose we have a material where the gap between allowable energy levels is much smaller. We call this material a semiconductor. Let's just show one row for the top energy band and one for the bottom energy band. In a semiconductor, the gap between those two energy levels are just small enough for thermal vibrations to allow an electron to sometimes jump from lower to higher energy levels. Now that the electron is in the higher energy level, it's now free to move around. This free electron leaves a vacancy in the bottom energy level, thus causing other electrons to move freely and occupy the empty space. So electrons in the bottom line move, while the top ones move as well. When the electron at the top and the vacancy align, the electron falls back down to the lower energy level. In this example, this semiconductor is not a very good conductor or insulator of electric current. We could change these properties by adding chemical impurities such as phosphorus, arsenic, antimony, and bismuth, which create extra available energy levels near the bottom energy band. This allows for more free electrons to travel between lower and higher energy levels, thus allowing the material to easily conduct current. Each blue sphere in this diagram represents a negatively charged electron, while the red sphere represents a positively charged proton. The locations show a red sphere without a blue sphere can be thought of as a hole with a positive charge. Since it's a hole with a positive charge, we could call this a p-type material. Similarly, n-type materials have the top energy band with free electrons. Both n and p-type materials conduct current easily and have numerous applications. For example, p-type semiconductors are used in passive applications, while n-type semiconductors are used in most technologies where conduction current is of no consequence. Now suppose we place n and p-type semiconductor materials together. The electrons from the N-type material will migrate into the P-type material, and holes from the P-type side will migrate to the N-type. So here's the process slowly. As you can see in the top band, electrons move towards the right, and same with the P-type electrons on the bottom. Electrons in the top energy band will then fall down to the bottom holes of the energy band. This results in a region with a net positive charge in the N-type material and a region with a net negative charge in the P-type material. This creates an electric field preventing additional electrons and holes from crossing over. This is represented by a charge difference between two materials and indicates if an electron were to travel towards the P-type material side, there would be an opposing force. Now that the basic principles of semiconductors are discussed, you may wonder how they are fabricated. To fabricate these electronic components, such as a diode or transistor, you must start with a semiconductor wafer. From this, the following manufacturing steps are oxidation, photolithography, etching, deposition and ion implantation, metal wiring, and packaging. Semiconductor wafers, as seen here, are usually made of silicon extracted from sand, which is heated until it reaches a high purity liquid. The hot liquid is then sliced into circular ingots, but has many surface defects, so polishing machines are used to even out the surface on the micron level, as they greatly enhance the precision and efficiency of circuits. This disc right now is not yet conductive, so a process to make wafers semiconductive is required. First, wafers go through the oxidation process, hence the name. Oxygen or water vapor is deposited on the wafer surface to form a uniform oxide film. This film protects the wafer surface during the following manufacturing steps. As seen in the slide, here's an example diagram showing the semiconductor cross-section. Now the building process begins. Starting with photolithography, this process involves drawing a circuit design onto a wafer known as a photomask and is analogous to developing photos taken on a film camera. With semiconductors, a photomask functions as the film while the light is the developer. Shown on the right is a semiconductor at this stage, and the right is a simple diagram and cross-section. In order to transfer the photomask onto the wafer, a photoresist, a material that responds to light, is applied thinly on the previous layer. Now, with the transmission of light, the pattern photomask creates a circuit on the wafer surface. Seen here. Now, there's a lot of unnecessary material on the wafer. So the etching process, which is employed right now, carves out only the designated circuit pattern. In this technique, there are two directions with sample preparations with ions: focus ion beam and the near parallel ion technique, which is generally known as ion milling. Their key differences lie in ion beam parameters. In the case of focus ion beam technique, a finely focused beam of high energy ions, commonly gallium with up to 30 kilo electron volts of energy, is used for precision milling in spot sizes of 50 by 50 microns thick, and preparing samples may take a significant amount of time. In contrast, the near parallel ion milling technique involves energies less than 20 kilo electron volts, and an inert gas such as argon is ionized and accelerated to form a broad, non-focused beam of ions, which interact with the sample surface. The kinetic energy of the incoming ions is converted into heat and momentum upon impact, breaking atomic bonds and ejecting material to remove thin layers in a controlled fashion. By focusing the ion beam across an area of interest, the exposed surface can be precision milled to a desired depth. Photolithography and etching processes are repeated several times on the wafer, layer by layer. To protect the etched surface, a coating is placed on these layers known as deposition. At this point in the manufacturing process, the semiconductor is not yet conductive. To give it electrical characteristics, ion implantation is also required. This entails the addition of impurities, as stated above, such as phosphorus, arsenic, antimony, and bismuth. And at this step, the wafer finally becomes conductive. In order for the circuit to work from the photomask, an electrical signal must be applied. This is known as metal wiring and bonding process. As the name suggests, a thin metal film is placed on the wafer. often aluminum, titanium, or tungsten, which allow for free electron movement in the desired circuit that you want. The semiconductor is now complete and needs to be encased in molding to prevent mechanical damage. This is known as packaging, and it is the last stage in manufacturing. Here, the wafer is cut into individual semiconductor chips and can be placed on a printed circuit board through chip bonding, where the contact point of the semiconductor chip is placed in relation to the contact point of the connecting substrate. This piece together now can be placed on the printed circuit board. Molding is employed on the newly formed chip, which is finishing the chip package to its desired shape. Now, the semiconductor chip is finished and can be implemented into electronic devices produced by known companies like Apple and Samsung. This concludes my presentation. Thank you for listening, and I hope you gained some basic knowledge on semiconductor principles and how lots of electronic devices are manufactured, as this process is not just limited to semiconductors. It can be seen in aerospace technology through, I guess, yeah.